It's a pleasure to welcome Tom Rondeau. So Tom and I were introduced by a mutual friend, and it turns out Tom lives in Burlington, and so comes through Hanover a lot. So over the last few years, we've gotten together and talked several times. And as time goes on, it turns out we have more and more in common in terms of associates and interests. So Tom lives in Burlington, Vermont. He did his undergraduate work at Virginia Tech in Blacksburg and got his PhD there in 2007. Did a postdoc at Trinity College, Dublin. And now he's sort of a consultant, also has a relationship with the University of Pennsylvania. And he's here in his capacity as basically the leader of the GNU radio project. He also helps to organize the annual conference, the GNU Radio Conference. And it's a pretty remarkable international effort to sort of open source radios. And he'll tell us about that. So welcome, Tom.
Yeah, thanks, Rich. Is this, yeah, I think it sounds pretty good. Sorry, I woke up Tuesday with a cold in my throat, so I'm going to try to rely on this. Usually I just shout really loud, but I'm going to try to keep it calm. Really happy to be here. So George gave you my introduction, so I'm just going to go straight into my presentation, if I can pull it up properly. There we go. So this is going to be a general overview of GNU Radio, but also a little bit more of the SDR space of research interest and topics. The first part of this, I'm going to go over kind of a brief history of radio and kind of why it's important. This kind of came to me, well, I have a general interest in the history of science and the history of radio in particular, so I've been doing a lot of work on that. So it's kind of a natural thing for me anyways. But one thing that struck me was I was on a panel session a few months ago, about a month ago in St. Louis. DARPA was holding a big conference, their Wait What conference, where they were kind of showcasing all of their technology. And they had a bunch of panel sessions, and I was invited to be on one on Spectrum. Now, this is DARPA, right, the Defense Advanced Research Projects Agency, the guys that brought us the internet and GPS and the Grand Challenge and the Grand Robot Challenge and robotic arms and limbs and lasers and like just some really cool stuff. And so we're sitting there going like, we're just doing radio. Like, what's so exciting about that? Like, who's going to come to our panel over people like legitimately talking about extraterrestrial life and colonizing Mars and, you know, really cool stuff like that? And then it kind of struck me like, honestly, they're probably saying the same thing about their field, and why aren't they going to talk about wireless stuff? Because, you know, this ethereal, ephemeral, invisible waves that we transmit and control through the air, you know, if you kind of step back from me dealing with it for the past, 15 plus years of my life, it is kind of wizardry. So I just kind of wanted to focus a little bit on that and explain maybe, there we go. Explain maybe just a little bit about why I think that this is some really interesting and cool stuff. This is somewhat where it all started, at least from a practical standpoint. So we had Faraday and Maxwell and those guys discussing it from a theoretical perspective. Hertz's interest, this is Heinrich Hertz's apparatus. This is the first time he'd actually shown electromagnetic waves in reality. Because Maxwell was very contentious whether or not his theory was correct. Nobody, not necessarily everybody believed it. And so Hertz and the other Maxwellians were really dedicated to proving this was correct. So as Oliver Lodge once said, it was ridiculously easy to produce high-frequency waves. We just didn't know how to detect them. And that's what Hertz did, is he figured out how to detect them. But this was down way, way low, like I think 6 megahertz is kind of the analysis of what Hertz was probably generating and detecting through his apparatus. But this launched a huge innovation in the technology of wireless. So along comes Marconi, who realized this technology, what it can be used for from a communications perspective. And so now there's definitely a lot of information and misinformation and theories and myths about Marconi and his role here, and maybe even his expertise and knowledge or understanding of what was going on. But the fact remains that he really did launch an entire empire of communications, wireless communications and wireless telegraphy just kind of based on almost the sheer will of wanting to do this once the theory, the kind of physics of it were proven. But even still, he was way, way down. So throughout this, there's this kind of spectrum mask down here. We're just going to kind of walk through it and see kind of how things changed over time. So he started off really early on with his low frequency and fairly uncontrolled frequencies at the time. Until this guy comes along, Edwin Armstrong, one of the most important inventors of the 20th century. He created what's known as a super heterodyne receiver, the basis of our radios for 100 years. Really the basis, the foundational technology that kind of made everything work from there. So he's able to bring about the wireless age by introducing these concepts like the super het receiver. So you're starting to push up into these higher and higher frequencies. Now, the amateur radio guys in here will know this, but if you're not familiar, I'm going up to 300 terahertz up here. 30 megahertz is considered high frequency at the time. We still call it the high frequency band. We've run out of superlatives to add to stuff after extremely high frequency and the like. But Armstrong is able to create this receiver that revolutionizes how far up in frequency we can get and the purity of the signals that we can get based on his experimentation for the Army. He also introduced to us FM radio. So FM was an interesting invention because actually even at the time he was told that it doesn't work. And he's sitting here, but look, I showed it works, right? And this guy Carson says, no, it doesn't work. Mathematically, it doesn't work. But what's interesting about Carson's math is that we still use it to this day to talk about FM. He was absolutely correct in his math, he just didn't understand what it meant. And it meant that FM actually worked, and the bandwidth requirements of FM were kind of based off of his analysis. Armstrong didn't actually really care about the math, he just knew what it was going to do and that it worked, and he created a system to make it work. Now, why was this important? As it says, static-free radio. At the time, it was all amplitude modulation, mostly voice going over, so AM radio, which is very susceptible to static noise, just noise in general. In particular, if you're trying to use it for police radio or public safety radios, car ignitions are really loud, as are many other mechanical processes. They're actually electrically very loud, and they cause interference. So the car that you're trying to use for your public safety system is actually your source of interference. FM is very robust against that, so that was one of the big inventions and innovations to move the concept of what communications was from the strict amplitude modulation into this frequency modulation. Which we now there's a really interesting story that I'm not going to get into about Armstrong and FM and regulations in RCA. There's plenty of stuff written on that elsewhere. But we are starting to move up in the frequency band. So again, we're kind of moving into higher and higher frequencies. So we now have the FM band from 88 megahertz to 108 megahertz. So really, by the time we're done with this conversation, we'll see how low frequency that still is. But it's still in use, still very much in use around the world. So that's part of what Armstrong is credited with doing for us. Now, pulling back, I want to try to see. Okay, so we have this technology. Marconi understood its use case from a communications perspective, but that was just the next generation of communicating long distances using wireless technology. Because we go way, way back in time to see different uses for communicating long distance. Does anybody recognize the thing on your left there? It's the semaphore system from France. So this is actually, the semaphores concept of the flags. You change flags in a certain way, and you communicate information. Those arms on top there would actually swing in different directions, and they were used to communicate information. This was actually deployed all around France during the French Revolution, used as a communication system, specifically a military communication system. Does anybody recognize the picture on the right? It's from Lord of the Rings. But it's based on actual uses of signal fire to signal information long distances. So as armies were invading or something was happening, you would light these signal fires to go long distances. Now what's interesting about this is how little information you can convey in a signal fire. right? It's one bit of information. It's either on or off. You have to pre-establish what on versus off means. But even still, back then, we were, years and years ago, we were still using this as a way to try to move information long distances. Now, this actually does, as opposed to all of our other wireless stuff, I did have to point out, this is optical communication system. So we're up in the terahertz region of comms, really. Here's another interesting thing. So that was a military application. So the military use of communications has been one of the strongest generators of technology and innovation in the wireless space. As I mentioned, the Super Het receiver was designed by Armstrong for the Army. This is another really interesting use case. Commerce. This wasn't the image that I wanted to pick up, but it seemed but it worked. So this is the cost of I guess the fish market in a specific area of India. This is just an analysis done a few years ago. I was looking for, there was another one for fairly recently that was the cost of some grain in Africa, I think Nigeria. I couldn't find the graph that I wanted, but this kind of shows the same thing. So the cost of a good before you had cell phones, the variation on that cost goes all over the place because the uncertainty, because you have no idea what the rest of the market is doing. You introduce cell phones to these regions, to these particular types of situations. Let's just say farmers in general. Now you have access to information. You can communicate and gather information about what's going on with the rest of that market. Now it's reducing the cost, the price of it, but it's giving you a much more, a higher certainty of, and lower jitter, essentially, variation in this case, of the cost. That certainty completely changes how you can design your market, design your farmlands, and the certainty that you can get for the cost of your good. Just revolutionizes what you can do from a market perspective by having access to information like this. So there's a massive commercial good that can come from this type of stuff. So we'll get to the social aspect of that in a second. But again, stepping back in time, we go to World War I. This is interesting. The generation of the Super Het receiver was the Army said, hey, we want to be able to communicate longer distances. Armstrong, can you build us something? And he said no. His real motivation comes from the airplanes. So airplanes were a fairly new invention, and as soon as the airplanes were invented, we figured out how to use them for war. Fly over a place and drop a bomb. Armstrong figured out, well, hey, there's a combustion engine in there. There's a spark plug in there. That spark plug generates a signal roughly around 10 megahertz. We had no idea how to receive 10 megahertz signals at the levels that they were being generated from this. His intention was, okay, what can I do? Can I build something? I don't care about comms. I care about, can I do over-the-horizon detection of airplanes before we can even see them to prepare for an aerial assault? It's almost the first application of electronic warfare, as we know today. So his intention was to build a system, and that's what became the Super Het, to detect airplanes coming over the horizon. World War II, obviously, there's a massive role that communications plays in World War II. Just from the soldiers themselves trying to communicate. But you can see, look at the comms system that's built all around this guy in the field trying to communicate to, I'm not even sure who at this point, but you can just see the size of that comm system. Does anybody recognize that top picture on the right? You guys ever hear of Huff Duff? If you've read Cryptonomicon, Huff Duff plays a big role there. High frequency direction finding. So these were gigantic systems, antenna structures. I mean, these are massive antenna structures to do high frequency detection, and the location of them all around the world was used to do direction finding of high frequency communication systems, basically trying to detect where U-boats were. Bottom there, is that people, hopefully, raise your hand if you know what that's, the one on the bottom there is. That's an Enigma machine. Huge part of the Allied effort against the Axis. So that was a German cryptography machine that was famously broken, if you've seen the Imitation Game, famously broken at Bletchley Park and used to properly detect where U-boats were going to be and where they were. There's a similar machine that the Japanese used, I forget what it was called now, Purple I think was the name that was applied to it. So the war in the Pacific and the war in the Atlantic were hugely influenced by intelligence gathering by breaking cryptography codes of information transmitted over the air. So we have all this stuff going on in VHF and HF communications during World War II. This is interesting because this is a Vietnam era communication system. The first non-vacuum tube man-pack. So that was an innovation. Vacuum tubes are amazing devices for linearity for amplifiers. They break really easily. So to actually do a solid state man-pack that you could carry around and not have to worry about replacing vacuum tubes. I think this was affectionately called the Prick 77 by the Vietnam era soldiers. We're finally getting up to VHF communication type systems. This is, it's still in use, and I believe it is a frequency hopped system. I don't think it's technically considered, but it does have a frequency hopping component to it. So there's some kind of new technology coming into to the system. This guy is rather famous, at least in my field. His name is Marty Cooper, and that's him making the first call on the first cell phone. Pretty ugly cell phone, but revelation at the time. Now, what's interesting about this? First off, we are coming up in frequency. We're now, the first amps, the first generation cell phone amps was right around 850 megahertz, something like that, plus or minus. But what's interesting about this, in this kind of story that I've been telling about the military uses of it, first real non-military invention kind of coming out of the comms, electromagnetic comms system in quite a while, as far as like a point-to-point communication services. So we're finally in the 80s pulling ourselves out of it being a military-only direction for radio and more into a commercial and industrial perspective. So we have that, and then of course follow that all the way through to our cell phones, the kind of candy bar cell phones, second generation, even third generation cell phones in all their different forms, from your Saved by the Bell Zach Morris device to your Nokia candy bar device in your hands. And of course, what we all know and love today, the smartphone. These are all Android devices, but we've got our iPhones and everything like that. So again, we're really starting to switch our focus to consumer applications, consumer devices for radio systems. But in this switch, and this is kind of where we kind of come back into to what we're thinking about with software radio. Even though we were very, very military focused in our comm systems early on, of course I've kind of left out radar and a whole bunch of other technologies, but just kind of from a comms perspective, very military oriented. As I mentioned, the man-pack, the first solid state man-pack, started to really get us into this realm of very densely packed RF circuits, RF systems. This guy, it's a black box as far as we're concerned from a radio technology perspective. There's no vacuum tube in here, there's no discrete component, no capacitors that I can pull off and tune, inductors that I can rewind, anything like that. It's this black box. It's a really nice and shiny black box, and it works really well for what it does. But we have no insight, we have no access to it. So that's kind of changed as well from our perspective of how many radios are in that device, as well as us being kind of walled off from it as technology has advanced. So we went from a stage of Armstrong sitting in his lab working to develop FM and the superhet and the super regenerative circuit and all those things to this point where we're talking multi-billion-dollar corporations necessary to have any inkling of what's going on inside. But it's still really cool stuff, like this chip. The AD9361, you'll see it talked about a lot in the software-defined radio. I'll explain what this is in a second, but that chip right there is that ADI chip. Now, look at the spectrum that we're talking about that one chip is capable of going over. This is basically 50 megahertz to 6 gigahertz. We have access to all of that as part of our radio spectrum today. Now, it's still this nice little compact chip that we don't necessarily know what's going on inside of it, but what comes out of it is raw samples, complex data samples of the signal itself. That we can get access to, and that's where we start to talk about software radio and what can we do from a digital numerical coding perspective based on a chip like this. So this has been pretty important as a single chip device that's allowing us to have access to so much of the electromagnetic spectrum. The next stage, though, is, I wanted to point out how small these things are getting. Now, this is the Be200 Mini. It's the USERP Be200 Mini. Universal Software Radio Peripheral is what it's called. Edis Research makes these. Now, Matt Edis and I go way back. Matt Edis kind of helped start GNU Radio, and I've been working with him for over 10 years. So you feel like you have an in with these things. He said he'd hook me up with a B200 Mini. Nobody can get their hands on them. They're selling too fast. That National Instruments that produces these can't actually make enough of them at this point to sell them, even to give one to me. So I'm stuck with this gigantic radio board here, as opposed to something that size. The story behind that goes, okay, we have that board there. It's really cool. We can do all sorts of stuff with it that I'll explain later in the presentation. But it's just so big, it's so unwieldy, it's just this gigantic board. So the guy who designs the RF for Edis goes home one Christmas break, he goes, you know what, I'm gonna go home and I'm gonna make a board that's this, what do you say, I think he said smaller than a cell phone. He's gonna make all the stuff we can do in software radio smaller than a cell phone. So the project manager, Ben, says to this guy, Shu, he says, Shu, don't even come back to me unless it's smaller than a credit card. So Shu comes back after Christmas break and he goes, ha, made it smaller than a business card. So that's where we are at today, 6 gigahertz of spectrum in that, completely open to us for transmit and receive purposes, that can fit inside of a wallet at this point. So that's pretty exciting. The next generation of technology, and honestly, feels almost impossible, except I've seen it work. This, I don't have an actual picture of the device itself. This is what was released from DARPA. This is a DARPA project called the RF FPGA. This is part of their public release of it, so I just throw that up there. But look at this. It goes from DC, from 0 hertz up to 20 gigahertz. And this thing is just a chip. And by the time it's released, it'll probably be a chip the size of the ADI part. Very flexible, multi-channel. I think it's like 4 channels that you can do simultaneously. So simultaneous access to 4 parts of 20 gigahertz worth of spectrum, like 200 megahertz or maybe even more bandwidth at a time. Absolutely unbelievable technology that can fit inside of a chip these days. Now, I talked about this black box. Again, this is still kind of walled off to us as far as the actual components. But this is fully programmable, and we get the raw samples out of it. So the samples themselves that we're going to get from the air or transmit into the air, we have full control using numerical processing methods. So that's really exciting. Hopefully we'll see that in some consumer products available to us from our hacker days soon. So we talked about the commercial, we talked about the military. Very strong, easily accessible what the military aspects of communication are. But there is that social aspect. Today, a lot of the communications, I was hoping to pull up the LTE signal from Verizon. There's 10 megahertz of spectrum that's almost everywhere in the world, or in the country, that Verizon uses for its 4G downlink. That carries so much of the data traffic that we use because the mobile phones are carrying so much data these days. And most of it is social-based. YouTube, video, Netflix videos, Facebook, all of those things are part of the social aspect of communications and what we're doing when we have these things in our hands. Now, I'm going to leave this as an exercise to the readers here to understand what is wrong with these two graphs. They don't make any sense at all if you actually look at the numbers. They were made at very different times, and the order of magnitude is like completely off versus like, what is it, petabytes per year versus petabytes per month or something like that. Basically, I put this up there almost as a joke to myself because we always see these graphs in the wireless field. We see these graphs about how much the data explosion is going to happen, and yet nobody actually has a clue how big it's going to be. Now, it'll probably tail off eventually. We have no idea what it's going to look like in the future. All we know is that it's growing exponentially now. So if you want to study the numbers here to see if they actually make sense, I don't think they do, but it's not really important. The important thing is this exponential growth that we can see and almost feel. I live in Burlington, Vermont. 60,000 people live in my town. I actually live in Shelburne, 7,000 people in the town that I actually live in, just south of Burlington. I have 4G on my phone, brilliantly fast. I get access to everything. It's almost faster than my home internet. I go to Philadelphia, barely get anything. I was in the Philly airport with a Pope visit. You couldn't even get online. That's how much of a spectrum crunch that these people are under. So congestion in those areas is massive. So that's the kind of social aspect that communications has on our culture right now. And one of the driving forces for new technology, new spectrum regulation, this push to, we're on 4G, we're already talking about 5G. 5G is already getting into actually it's even getting into the common, like the lay press, people starting to talk about 5G that I've heard about. 5G really isn't supposed to be deployed until 2020, but we're probably actually going to get there sooner than that. So all of those things, that's really what excites and kind of motivates a lot of us in this comms world. As boring as we kind of think it is just because we're so enmeshed in it, the history and the impact of it on our community from social to military to commerce is massive. So I've showed you these amazing things. All of the stuff that we've been able to do and we can do with radio. All right, where does the software come in? Why am I talking about software-defined radio? So these are part of, these are kind of for my things because I kind of wear these hats at different times. So as leader of a GNU project, GNU Radio, I have that hacker or tinkerer, depending on which side of the culture you split on. But these are things that I want to hack on. I want to build. I want to tinker with stuff. I want to explore it. I want to figure out new ways of communicating with these little black boxes and make them work for me. To think about what's going to happen in the future with our technology and with the need for more spectrum and more interesting use cases for comm systems. That's what the hacker in me is interested in. Obviously, that goes directly into the engineer, but that's more of, I kind of separate those two almost from like a tinkerer to product development cycle. But if you think about that multi-channel 20 gigahertz capable RF FPGA that can be tuned and tweaked and manipulated, there's filters that you can set in there, all those things. How do you control that? So there is a software perspective of even an AI. My dissertation was actually in artificial intelligence and wireless communications. So even using machine learning or AI concepts, can we use that to have this kind of broad control over the waveform, over the receiver and transmitter? So how do we kind of wrestle this complexity into something that we can use and then make good products out of? Improve that the cell phone, improve our communication systems, make them more power efficient. Right? Get rid of or use the battery for something else besides the comms. What kind of aspects of it are there? The mathematician, so every now and then I play like I'm a mathematician, but there is this aspect of that complexity and what can we do from a math perspective to understand comms better. If you actually look at the kind of communications theory, the classic paper, the famous paper that kind of solidified what we do today is from Claude Shannon, A Mathematical Theory of Communications. So he really laid out the basic math of it and started information theory. Huge amount of math in there. If you look at like the hard part of communications these days is the receiver, synchronizing your signal. So I have two radios sitting up here. They're running two free-form clocks. They're not disciplined to each other. They don't know each other's frequency, timing, anything like that. So when I transmit from one to the other, they're going to be off in frequency and time samples. How do I actually establish my communication system based on that? There's a lot of math theory that goes behind that. And we've made compromises in hardware to make it work because we can't actually perform the real mathematics just directly in the hardware. Computationally, we can. Numerical analysis tools that we have today, the amount we can do in digital signal processing is quite amazing. And it changes, not only that we can go back to the pure comms theory, it actually changes how we think about communications. If we're only limited by our numerical complexity, we can do a lot more interesting things with those signals. The academic part of me, though, coming from an academic background, I think the educational perspective of this is astounding. The ability to look at a signal, play with a signal. Like I said, one of the hard things to do when you're selling communications theory or selling the idea of the importance of comms is the fact that you just can't see it. But every step of the way in a software radio system, you can see and interrogate and change and manipulate that signal to get a really good feel for what's going on inside there and how to play with it, how to improve it, and how to finally decode it into information. So I've actually been really, it's one of the things that I'm most proud of when I think about my 10 years working on GNU Radio, is that I really feel like we actually have changed the educational concept of teaching communication systems. You can hear it in the way people talk and the dialogue and the vocabulary they use is coming from the software radio perspective of looking at and playing with and really exploring signals through real hardware over real channels, as opposed to just simulation and textbook images of perfect signals. So all those are going into what I think is the importance of a project like GNU Radio. So let's go back to what the basics of software-defined radio means. So you'll hear me say software-defined radio or software radio. Some people like to have a distinction between those two. I don't really care. So I'll say them kind of interchangeably. The ideal SDR, or software radio, is just interaction straight from your numerical processing system, like your CPU, and the antenna. So those two things in between, the ADC is analog to digital converter, the DAC is a digital to analog converter. So this is just converting between the analog domain that the antenna understands and the digital domain that we're going to process in our numerical processing units there. So this is an awesome idea. It's a very attractive and enticing idea. It just doesn't work. The problem is when you're dealing with signals coming in minus 110 dBm. That's a very, very, very small signal. A small enough signal that it's not actually going to trigger your analog digital converter. It's not going to know that that signal exists. So you've got to amplify it somehow. So you've got to put in an amplifier in there. The fact that to receive the signal, the bandwidth, if you're talking even Wi-Fi, is up at 2.4 gigahertz in frequency. To sample that, you actually have to have a system with a bandwidth to cover up to 2.4 gigahertz. Ideally, you'd want something that could sample at that speed. There's a little mathematical trick called bandpass sampling that we can get around that, but you still need to have the bandwidth to be able to see that signal. Most systems don't have bandwidth that goes over that length of spectrum, or up to 60, 100 gigahertz like people are talking about today. So you have to have some kind of digital converter or analog conversion of the frequency. So some kind of a super heterodyne receiver, just some kind of heterodyning receiver that moves it from the RF frequency down to close to what we call baseband or 0 hertz before the analog digital converter can actually even see that signal. So we have all these things that go into it. So really what we're talking about today, this is more like what our software radio perspective is today. We have this thing we call the RF front end. And this is what's doing all that, the amplification and the mixing. It's called a mixer to do the heterodyning, to move from RF to DC or from DC up to RF. So all those are going to happen in the analog domain still. So we have to build systems that can do that. And that goes back to what I mentioned before, that ADI chip sitting there. That's basically that RF front end is what happens in the ADI chip. So this ADI chip does the signal disciplining in the analog domain from 0 to 6 gigahertz, roughly, to just get us into a realm where we can sample it and we can get it through our analog digital converters. So we still have that going on in that front end. And then we're often coming out of this thing. I think this thing has I think its sample rate of the analog digital converters, actually it's this one I think is variable, but it's like 100 megasamples per second. So you're dealing with 100 million samples per second. Each sample is actually 32 bits. We actually represent it as two 16-bit numbers. Actually, it might be 14, two 14-bit numbers, I forget exactly. But still, that's a large amount of bandwidth to pass through to process. And we're going over USB here. So if you run the numbers, you can't get 100 megasamples per second at 32 bits per sample across the bandwidth of USB 2. Actually, you can't even do it with USB 3, I don't think. I have to double check on that. But so we're limited from that perspective. So we often have things that we're going to do in the FPGA. So FPGAs are brilliant for doing high-speed digital signal processing, with some more specialization, right? It's harder to program an FPGA. It's harder to change the programming in FPGA live. So it's kind of more of a firmware type idea. So in here in the FPGA, we're just going to do some of the high-speed sample rate signal processing, more filtering, and sample rate conversion. So we're going to downsample from 100 megasamples per second to 25 or 10 or 5 megasamples per second. Things that we can actually pull over the bus that we're actually going to be using. So once we do our basic disciplining of the signal from there, these are kind of things that we're hoping are universal for most signals. So most signals that we're going to do, as long as we can get the bandwidth and the filtering around it correct, all the rest of it, we finally get into our real software processing system. And this may be a DSP, might be a general purpose processor. There's other like baseband processors out there, which are kind of like more application specific designs for computing systems. Graphical processing units are not out of the question. They're often used for some of these purposes. But it's a much more fluid software, reconfigurable, flexible system that we're finally getting the signal into. So in our case, in kind of the GNU radio world of things, the usurp does all the way up to that FPGA DSP, and then we move it over to a host system. And now that host system is often a laptop or a desktop or, like in this case, an Android device. So I have a tablet that can run GNU radio to do its processing there. And that gives us a huge amount of flexibility. Well, why does this matter? This is kind of the part that's often been missing from communications education, is what goes on between when you transmit and when you receive. It's all these multipath analysis tools and link law, what am I thinking of? Like free space loss models to do this thing, but they leave out a lot of, they're approximating a lot of things, they're leaving out a lot of stuff. So from the software radio perspective, I like to start with AWGN. So it's additive white Gaussian noise. AWGN, very common, noise happens in the receiver. It's just a thing that everybody has to deal with. As well as I mentioned, 2 radios running on different clocks. You've got this whole offset of frequency of timing that you got to solve. So that's like the basics. Like if you can't communicate through that model, you're never going to go over the air. So that's like your number one thing to start with. Then you actually want to add a real channel, right? So when I'm talking, you're not only hearing me through the microphone system, but you're also hearing me, directionally, audially, from an audio direction perspective. It's bouncing off the walls. It's hitting you at different times and at different phases. Same thing happens with radio signals. So I'm going to emit a signal. It's going to bounce off of things. It's going to change phase. It's going to interfere with itself. It's going to interfere with its previous symbols that are sent. All those things, these multipath environments. As well as when I'm moving, right? We know Doppler spread of audio. You can hear that, right? The train motion, all those things, those kind of classic things. Redshift of planets, those types of ideas. Same thing happens again with radio waves. So Doppler effects can be located within that channel model as well. One of the things that's often left out of our kind of educational concept of communications is the hardware impairment model. So we don't really recognize the fact that we're pushing a signal through this device. That antenna has properties to it that are going to distort the signal. The PCB itself, all those components there, the RFIC, have linearity problems. We have to address those as well. So we can actually build up this model from a software perspective. What's really nice, though, is that once we have this, once we kind of solve this problem, we can say, okay, given this hardware impairment concept, these kind of channels, all of this information, all this distortion here, we're ready, and GNU Radio allows you to almost instantaneously go from that simulation model to over-the-air. So now we're actually ready to figure out if this thing is going to work in an over-the-air concept. So we have all this stuff from learning and understanding and playing with the signal all the way up to actually transmitting and putting something out in the field. And GNU Radio and these usurps have been used from everything from prototyping waveform to deployment into real scenarios. All right, won't spend too much time on this, but this is just kind of like the bullet points of what GNU Radio is and does. So it is a framework. It's a project with a community and the framework and the library of blocks. So we'll see that. I'll put this up here kind of more for just for completeness. We're actually going to see in a little bit when I actually pull up GRC, so let's just skip past this. Although I think the important point to list that I won't show you as far as the software goes is being open source, we've developed a community around it. So a community of users and experts and developers, people who just like to do this for fun, high school students that are just learning, to people who are working in the field on on real radio systems, experts that actually help us out and understand stuff. So huge amount of insight from that gigantic community of users. Let me skip this too for the most part. This is kind of a cartoon of what a GNU radio application looks like. What you're going to do is you're going to string blocks together to make a flow graph, we call it, or an application where data comes in from a source. So if I'm receiving stuff like I am right now, this is my source, and it's going into a GNU radio graph, and it's being processed by all these blocks, and we're doing signal processing manipulation on them. We have a message passing system, so this block can actually communicate back, tune something. Maybe we want to adjust the signal levels, change the gain, or change the frequency. Lots of information that goes on through here. If you want to know more, this kind of explains what a block looks like. So every block is generated this way, where there's this work function that does all the signal processing. So you kind of program your work function in there. Has this message handler queue. Again, details here for those of you who are interested. If you're really interested, we did just, there's a book that was just published where I was asked to write a chapter explaining GNU radio. So if you're really interested in the details of what happens in the scheduler, that's kind of the go-to, I think, for understanding that. Yeah, again, I don't want to spend too much time on this because I want to say here, all I'm going to say here, again, slides will be available if anybody really cares about them. We have 3 models for moving data around. So the data streaming model, that's what we're going to see when I run this thing live. You're actually going to see mostly the data streaming model, where it's just data just flowing through a system. So you're going to take that data, you're going to apply whatever signal processing algorithm to it. You're going to multiply it by a complex sinusoid. You're going to filter it. You're going to perform an FFT on it. Whatever you want to do on that signal in the streaming model. The tag model, this one's a little bit more complicated to get into from me just kind of giving you the brief overview. But I did want to mention that this tag model allows you to annotate samples. So every sample can have a tag associated with it that tells you something like maybe the timestamp. So from a GPS, this actually has a GPS unit on it. I can actually get the actual timestamp of a sample, and I can save that into a file. So the tag kind of puts metadata on top of your signal so that you can store that and save it, which is great for scientific use purposes. And really what it was kind of designed around was to help us save information like what's the frequency that signal was captured on, what's the gain of the signal, so we can have some understanding of where it came from. Now this is kind of the cool kind of new feature, fairly new feature of GNU Radio, this message passing system. So it's kind of a command and control type layer. So I have, in this case, this is a real GNU Radio flow graph. So I have this source here. This is bringing in samples from a USRP device like I have down there. And then I'm just actually displaying it in frequency. So if I have, this is actually better. So I have it being displayed in waterfall and frequency, and I'm actually filtering it. So I'm going to make sure I'm rejecting some adjacent noise here. Doing a wideband FM receive on it. So I'm actually going to decode FM audio, an audio signal, and then I'm going to show it again in the waterfall and the frequency sync, and then you can listen to it if I ran this thing live. But I also have this message passing system here, where these connect back to the UHD, and when I click, so here I am, when this is running, if I double click on this, that actually emits a message to the USRP that says change the channel to what I just clicked on. So I actually have this meta control system here that I can just play with, so I can move the signal to wherever I want it to decode the signal of interest. So this is actually a FM audio signal coming across at 89.9 megahertz, some station that I found, that I'm looking at in frequency. This is frequency and time. Here's the audio decoding of it. And this is hard to see, but this is actually the audio footprint, spectrogram it's called. of a decoded FM signal. So that's pretty fun. Let me actually pop there. So this is kind of what we were seeing before. I don't know what that one is. So that guy that keeps coming and going, I have no idea what that one's about. That signal there, as I move the microphone, so that's actually the microphone being modulated and transmitted over the air. So I'm actually capturing that here. Typically what we do in our conferences when we get a bunch of people together, they come with their board, their USERPs or their other RTL SDRs as they're called, little USB dongles that are like $15 to buy. Challenge is find the signal, decode it, and if you can, retransmit on the same frequency and see if you can inject the signal into the wireless mic. So eventually when I'm talking at one of our GNU radio conferences, somebody will figure out how to hack into the system and override what I'm saying. Just fun. We didn't do it the last time. Usually it's an FM signal. That's not FM. I'm going to say that's GMSK. I think it's Gaussian modulated, but I don't think it's FM. So this is actually a digital microphone. So it'd be actually harder to figure out what's going on inside of this microphone. The one that we had at GRCon 15 in DC, really brilliant, like great new building, the CSIS building, really fantastic modern equipment. It actually had what's, if you're familiar with PSK phase shift keying, it's modulating information in the phase of a signal. It actually had 8 PSK on modulating the digital waveform. And actually nobody was able to break it. So we couldn't actually break into it at GRCon, which is kind of disappointing. You can see some other signals going on here. As I mean, we're kind of in a dead zone in this building. The only one that I was able to really pull out was the microphone that I'm transmitting here directly. I was hoping to see, up here we should be seeing an OFDM signal. That's the LTE downlink signal from Verizon. But you can see here, oh, there's one. Oh, that's good. That's LTE uplink. That's probably my phone, actually. That's the uplink signal of an LTE signal that we can see here. So that's the kind of, so once we have that here, and here, let me pull over. That's not going to do it for me, yeah. It won't let me, it's not going to do it for me. There we are. There we go, okay. So all I'm doing here is running a flow graph, this GR phosphor flow graph. So just usurp source into the sink. Here's another one. This is kind of like what I was showing you before. Pulling it from the usurp, let me go ahead and play this. So this is now loading up that. So this is pulling down signal there. And it's at 444 megahertz. Tune this guy. And then hope this actually works. All right, so yeah, now you can see up there. So as I speak into this, this is actually capturing it from here, transmitting as FM over this device and being captured over there and demodulated. You probably won't be able to hear it, but if I turned up the volume on my, probably need to turn up the gain. Yeah, so can I hear it? You can barely hear it, but it's coming. There we go. Now I'm overloading the receiver. So now what's amazing about this, let me actually turn this off. What's actually amazing about this is I put together this application in a hotel like a couple weeks ago, like just before this Wait What conference that I was at in St. Louis. I think I was actually in France. I was just doing this. I was there and this whole thing. This is a thing that was an entire lab's worth of work about 10 years ago. And here I am with a stupid little $200 Android tablet. Now, that thing cost $700, but the computer itself, just a couple $100. And the amount of signal processing that I can do. FM is actually fairly trivial, but it's the easiest kind of first application to do. But the amount of power that you get in this kind of a setup, right? I mean, you just kind of walk around with this, and I've got whatever I want to do, frankly, with the electromagnetic spectrum kind of in the palm of my hand, almost literally. So that's a real big innovation in the space of comms from our understanding, from the educational perspective of it, and the ability to just play around with it. So let me go quickly through these. This one I could spend a lot of time talking about. This is a really fun experiment that happens. NASA sent out this ISEE probe about 40 years ago. Went around the sun. We learned a lot about the sun. Then they redirected it into a comet orbit. For a long time, it was everything we knew about comets came from that probe there, that satellite, which is renamed the ICE-3. Comet orbits are weird, right? They're these weird elliptical orbits around the solar system, and we forgot that they come back. So last summer, it came back, and NASA was like, oh no, we don't know how to talk to this thing anymore. They decommissioned the ground station. They had no hardware to talk to this guy. This ragtag group of guys here get together. That's the only one that I know personally is the one kind of in the dark, mysterious one in the back is Ballint. They get together, they raise out $160,000. They take a USERP-2, similar to that, but kind of a box, Ethernet-based, brought it down to, that look familiar if you've seen GoldenEye? That's the Arecibo Observatory in Puerto Rico. It's the largest single aperture radio dish in the world. Plugged in a $2,000 radio into that thing and started talking to a satellite that was 15 million kilometers away with GNU radio. They did this within weeks. They had full control over that system. They could hear it. They could send commands to it. The one thing that was disappointing is it had absolutely no fuel left in it, or if it was just completely frozen. So we couldn't actually change its orbit. So by the time it came close to Earth around August of last year, started going back out in its orbit. They started to apparently get desperate, so they started sending it commands a little too fast, and they fried the microchip, as far as we can tell. So unfortunately now it's a dead piece of metal floating around this comet orbit of the solar system. The idea was if we could move it, if we could actually change its orbit, we could get it back into an Earth orbit and just have it kind of as a citizen science platform to do telemetry information to learn about how satellites work. If those colors look familiar, they called that McMoon because the ground station that they built was out of an old McDonald's in Mountain View, California. So really fun project. Here's another one where GNU radio was used in the DARPA Spectrum Challenge last year. About 98 teams competed for, I think, like a $25,000 and a $50,000 prize. So this was, trying to figure out how we can better use spectrum. What kind of new waveforms could we do to share and coexist in the spectrum? DISPAN, IEEE's Dynamic Spectrum Access Networks is a symposium. They had a similar spectrum challenge this year that was actually brilliant to have 5 teams and to see kind of what they learned and what they innovated for learning how to use spectrum. Most of these were based on GNU radio as well. I know a few people here that I talked to today are familiar with Juha Virtanen from the Haystack Observatory. So these are some of his pictures doing ionospheric, ionospheric sounding. So space science is a big thing that we can do with GNU radio. This is, I think, amazing. Right? It looks like a photograph, but that's actually radar. We're actually using radar to image the moon using software radio. I think GNU radio, Juha does most of his stuff in GNU radio, so I think that was it as well. Here's some fun links if you want to go and see some of the more infamous uses of a project like this. And this is where we do get asked questions about what does the FCC think of GNU radio? Because when you have this kind of control over the spectrum, you do open yourself up to interesting attacks and problems. Some of the car hacks that you heard about last year were actually done using GNU radio to talk to the car, or the past year. This one, let's see. Oh yeah, the Siri. If you heard about the Siri hack, that was actually done using GNU radio. So some interesting things that can happen because of this. And then we'll finish. This is I already showed you this application, but again, using Android, our ability to use Android to process stuff gives us a huge new platform, and I think lowers the cost and lowers the barrier to entry for users to actually get access to the spectrum, which I think is going to be important for new technologies and new concepts. So after all that, we started off with Heinrich Hertz's famous apparatus proving Maxwell's equations and proving electromagnetic waves. Someone asks Professor Hertz, what are they good for? That was his only answer. Hopefully, you've seen and have known of all the really interesting stuff that we have been able to do. The trillion-dollar cell phone industry that's out there now, all based on, that kind of started with his experiment in Karlsruhe about 120 some years ago. All right, well, I should have finished up earlier, but we have, I think, room for a few questions. Otherwise, thank you. So there's multi-parts that, to answer that. First off, no, we actually have a very good relationship with the FCC. I know many people at the Office of Engineering and Technology. We're good friends. They actually love this kind of stuff. Now they're scared of it, but they love it because they want to see new technologies, new access to spectrum, new thoughts around it, and this is what's going to help us learn that. This kind of stuff is helping us understand that for the future. So they love that idea, but they are, concerned about the possibilities of what you can do with it. Never to the point of actually talking about regulating us or stopping us from doing anything. The second part of that, though, is it's because they really can't. They have gutted their enforcement bureau. I can't wait till the next time I get to go to Manhattan. Apparently, the enforcement bureau of the FCC doesn't work on the weekends anymore. So the pirate radio stations on the weekend in Manhattan apparently just take up every single free FM station. So, no. The closest legal problems we have is that guy Bolland. He goes all around the world doing all sorts of experiments. And he was in, I want to say Venice at one point, with a whole bunch of usurps out near one of the canals, and he was doing all sorts of stuff with it when the Italian police came up to him and started questioning him. And by the time they were done, they were exchanging business cards, and they just thought it was a blast what he was doing. So most of the time, we're fine. I do want to point this guy out. This is Bastian Blossel. Sorry. Okay. So Bastian is a student. He was at Ilmenau. I think he's now, I forget, he may be Louvain now. Anyways, he's an Austrian guy who's done a lot of great work for GNU Radio and for side projects. This is the FOSDEM conference from last year. It's a free and open source software developer European meetup. Like 8,000 to 10,000 people come out for it for the weekend in Brussels. It's actually quite an amazing event. We have a SDR dev room that we hold. He showed this slide because what he had done is, if I remember the story correctly, the RDS system of FM, so the RDS is the radio data system, so you can actually, when your FM receiver shows the song title and the artist, that's coming over the RDS system. It's like a digital communication system. There's actually emergency codes that you can transmit on those, and he worked that out. He was actually apparently, like, as they were driving to FOSDEM, he was like, hacking that stuff together in the car. Unfortunately, this guy in some small town in Germany used that and broadcast out a terrorist attack, which did cause some people, not many people actually saw it, but it was still, So Bastian actually took the code down. Not that necessarily stops code from getting around, but he's like, no, maybe we shouldn't actually have that stuff out there. But he did make a big point of disclaimer of, like, please be responsible with this stuff. And at the end of the day, all the technology that we can do to prevent this stuff, to work on it, we're not going to stop it, right? We just have to be good citizens just to an extent. And there are going to be bad actors, and there's a whole social and political aspect of it as well as the technological aspect of it.
So Tom, let me just jump in. People can get the software by doing a search on GNU Radio.
Yeah.
And the receiver kits, the receiver transmitter kits, where are those listed? Where do people? Yeah. So thank you. Yeah. So GNU Radio, it is a free and open source software project. So it's on GitHub. It's on GNURadio.org. It's really easy to get to. Completely open source. Like, everything we do is out there. All these side projects, like there's that phosphor, the really colorful, pretty graph I was showing. That's what's called an auditory module. So that's something you can go on and download and install, and it works with GNU Radio. This is I mentioned this USRP from Edis Research.
and they're a commercial company that build and sell these. They were acquired by National Instruments, I think in like 2010 or something like that. So they're an NI company at this point. So you can get, you can actually get NI branded usurps, or you can just go straight to Edis Research and buy these. This is their lowest cost one. Right now, this is, like I said, $700, which sounds expensive to an individual, but for a research lab, this is dirt cheap. The real-time spectrum analyzer I was showing up there, that's like tens of thousands of dollars for, now, you're getting a calibrated unit when you buy a real-time spectrum analyzer. So it's uncalibrated, but still the amount that you can do with this versus what, so for $700. But they have a whole product line from $700 up to like $4,800 for like their PCI Express-based unit that can do 120 megahertz simultaneously, serious amount of power. They have an embedded system where it's just like a brick that you just carry around, and it does the GNU radio on the processor inside the embedded system. I call it GNU radio in your pocket because you literally just walk around with that thing doing stuff. I did want to point out from what George said, there's a company called Noolec. If I can find it, yeah, here it is. Noolec, N-O-O-E-L-E-C. They sell this thing for, in one-offs, it's like $17. And this is a receiver only. It doesn't do transmit, just receiver only. From about 30 megahertz to 2.5 or 2.1 gigahertz. So you get a huge spectrum that's accessible for like, for less than $20. Now it's less than $20, so the RF isn't great. But in my experience, it's better than you would expect for that much money. So that's actually a really cool thing. This is actually technically a TV receiver, but there were two guys, Ballin was one of them and Sylvain was another one, kind of figured out that you could just actually like toggle a bit over the USB line to turn it from a digital TV demodulator to a straight IQ sample. So you're just pulling off complex samples from it at that point. And we have direct access to that in GNU Radio. You just install the GR Osmo SDR project and you get access to this stuff. And then there's a huge range in between from the $700 down to $15. Some receive only. There's only really one other transmit-based one, and that's called the Hack RF, but for about $300. So there's a wide range of these devices out there that you can get access to. So, you're paying for the hardware. The software is free, but still well within the means of a research lab to just you want to play around with this stuff at home just to see if it's exciting to you for $20. Yeah. What's the typical distance range? Yeah, so that's one of the reasons why the FCC doesn't bother us too much, because these are technically test equipment. They're not built or rated to be products. So this is like, I think 20 milliwatt output power. All of them are under 100 milliwatts of output power. This, I believe, is just 20 milliwatts. Range is kind of a weird thing because it really depends on the type of modulation. But you're talking about building ranges to hundreds of feet at most kind of type thing, unless it's like line of sight for a very specific type of modulation. All right.
Well, thanks, Tom.
Thanks.